Okay, so we still have the final 5 pages. So this is our final ideas for the Bernoulli equations, because we actually know right now the flow under rotating. So if we still we write the Euler equations based on the different directions, is follow the radial directions. Okay, so as we know, this is a rotation axis, and we can apply the different angular speeds, and we try to observe how the fluid surface line changes. Okay, and you can try to image that the high speed omega will have the large different changes in the liquid surface line. Okay, so but how to calculate? So this is our final formula for the rotating flow, and the difference compared to previous is here. There is the minus. Usually we always say that the P plus gamma Z plus the 2 over rho V squared. But in here, there is the minus. Okay? So first, we know the AR is equal to the minus V squared divided R, right? And we know the V is equal to R omega. So I put the number R omega replaced by the velocity. So in here is the minus omega squared R squared and the omega squared divided R. And we only have the minus R omega squared, right? And then we put the in here. So we have the AR is equal to minus R omega squared. But the left hand side we have the D and the dr, but the right hand side we don't have. So again, I do the integrations, push into the right hand side. So here is the minus omega squared, and I can have the dr squared and divided 2, right? And we also say and the dr, and as I mentioned, the omega didn't change when the radius length changes. So we can also put the omega inside the differentials. So we can rewrite to minus dr, and inside we still have the omega squared R squared, okay, and divided 2. If you have this formula, and then you can replace the right hand side by these formulas. So we can rewrite the Euler equation by the dr P plus gamma Z, and the right hand side is the minus rho dr omega squared R squared divided 2. And we also say that the flow is incompressible flow, so rho can put inside. So minus dr rho omega squared R squared divided 2. So you can combine two sides together. Okay, so finally we know dr and the P plus gamma Z minus, because this is a minus, and you move the left hand side to the right hand side. So it still have the minus 2 over rho omega squared and the gamma squared is equal to 0. So in that way we know the P plus gamma Z minus rho 2 divided 2 over omega squared and the R squared is equal to constants. Okay, so notice that there is a minus, okay, not the positive. So it's a P plus gamma Z minus rho 2 over omega squared and R squared. Okay, so how to apply these equations? Okay, so currently we know if we apply the omega rotational speed is omega is equal to 4 radians per second. And after you apply the omega angular speed, please find the elevation difference between the liquid at the center and the wall. So that means this is Z elevation 1 and this is Z elevation 2. So the difference, so we would like to know how difference Z2 minus Z1. Okay, so we need to find out the solution for these problems. So this is a rotating flow, so we follow the Bernoulli equations of the rotating flow. So this is 1 and this is 2. So we have the P1 plus gamma Z1 plus, sorry, not the plus, so here is the minus, right? And the 2 over rho gamma square R1 square is equal to P2 plus gamma Z2 minus 2 over rho omega square R2 square. Okay, so you take a look, this is a rotational axis and 1 point in here. So we don't have the R1, right? Because R1 is close the point 1. Okay, so we don't have the R1 is 0. R1 is the radius relatively to the rotation axis. And then, so we don't have the R1 in here, so this is equal 0. And the point 2 and the point 1 is pulse on the air. So the gauge pressure is R equal 0. So we don't have the P1 and we don't have the P2. So you take a look and make the summarize. So we summarize the formula in here is gamma Z2 minus Z1. Okay, I move this item to right hand side and take this item to the left hand side. And then this is 2 over rho omega square and R2 square. Okay, and we know the gamma is rho G. So in here we only have the G Z2 minus Z1 and the rho right hand side cancel out. So we only have the 2 over gamma R2 square and the gamma square. And then D2 minus D1 is equal to 2G over gamma 2 square, gamma square. Okay? And we know the gamma R2, where is R2? R2, because the total length is 0.5, so the R2 is 0.25 meters. And we know the omega is 4 radians per second. Okay, so we can compute the answer. Here is 0.25 square minus multiply the 4 square and divided the 2 times of the 9.81. And then you can compute the answer. So 0.25 square multiply the 4 square is 16. And divided the 2 and divided the 9.81. So the answer is equal to the 0.051 meters. Okay, so the key knowledge in here, we just follow the Bernoulli equations based on the rotating flow. Okay, so this is very important equations. And the second, as you see the function in here, this is a liquid surface line, and the shape looks like the parabolic. Okay, parabolic. And what is the parabolic functions? Like the y is equal to ax squared, right? And a is control the curvatures, is thinner or fat. And we have the ax squared and the y. So compare the formula showing here. So we have the delta z changes as function of the r squared, gamma squared, and the 2g, right? So the r is similar to the x directions. So the constant value is omega squared divided 2g, and this is r squared. Okay, so this is normally to control the shape, the curvature shape of the liquid surface line. So actually, you know, if I change the different omega angular speed, and the delta z will change also. And the relationship between the delta z and the omega is a positive relationship. Okay, omega larger and the elevation difference also increase. Okay, so next semester we have the one laboratory experiments. We call that is flow test experiments, and this is our instrument. Okay, and you see there are some pin. The pin can measure the water surface elevations. Okay, so this is the idea as you see the movies. Okay, and the flow test experiments, we have the forced or free. So the upper, right now the example is show that the forced flow test, and you just check the bubble to level in your instrument, and then we have the pin, and then we adjust the different angular speed. So we have a different angular speed, and then we see that the water level line changes. Okay, and still change the different speed, and the water line change also, and they use the pin to measure the elevations in different locations. Okay, so you can adjust the pin to measure different location elevations. So it is very simple, because we know the curvature of the liquid surface is follow the delta z is follow the omega squared divided 2g and the r squared, right? So different location is different r location, and we have a different elevations. For this experiment, we just adjust the different angular speed and observe the level, the curvature changes. Okay, so it's quite simple. But why we say that is the forces? Because we have additional rotation and the people can control. But the button, we call that is free. Why we say that? So first we fill the water on the tank, and then we remove, and then the water is trying to flow out, flow into the hole, and then you see there are some voltages, right? So in that way, we call that this is the free, because there is no any external angular speed. We just remove we just open the hole, and the water trying to flow into the hole. There is no external force. Okay, and then you see the curvature of the liquid surface is different compared to the false test. Okay, so in this experiment next semester, you just plot the curvatures, and you have a different omega, right? And you need to plot a different curvature, and you feel different water highs, and you have a different curvature lines based on the different water heights. Okay, so this is the experiment next semester. So it's the final page. So in that examples, the rotation axis is in here, not in the centers. So we have the U-style tube, and what the answer we need to what the question we need to answer. So first we have the angular speed at radian per seconds, and they require you to answer the new levels of the water in the tube. So after rotations, and how change of the Z1 elevation may be changed, right? And maybe elevation will change to the Z2. So the 1 and the 2, they are the initial point. So how change after the rotations? How change it is? Okay, so because this is a rotating problems, so we write down the rotating flow for the Bernoulli equation P1 plus gamma Z1 minus, remember there is the minus 2 over rho and V1, not the V1, R1 square omega square. And the right hand side is P2 plus gamma D2 minus 2 over rho R2 square gamma square. Okay, again, so this is exposed on the air, so we don't have the gauge pressure location at the P1, P2. Okay, so, and then we know the R1 in here. Okay, R is the length relative to the rotating axis is 18 centimeters. So we change to the meter unit. And the R2 is 36 centimeters, so 0.36 meters. Okay, so we just take this reorganize the equation. So we put the gamma D2 minus Z1 is equal to 2 over rho, okay, 2 over rho and R2 square omega square minus here R1 square omega square. Okay, and then we know the gamma is equal to rho g. Okay, so Z2 minus Z1 is equal to 2g, because the gamma is equal to rho g. So rho and rho cancel out. So we only have the g and then move to the right hand side. So g is here. And the omega square is the same value. So I take outside. So inside we only have the R2 square minus R1 square. Okay? And then you can put the number inside. So 2 times 9.81. And the omega in here is 8 square. And here R2 is 0.36 square minus 0.18 square. Okay, so you can use your calculator to compute the answer in here. So 0.36 square minus 0.18 square. Okay, and then multiply 8 square divided 2 and divided the 1g 9.81, and the answer in here is 0.317. Okay, and the unit is meters. So we take a look. We only have the one equations, but we need to answer the questions is the new levels. So we need to know what is the Z1 and what is the Z2. But we only have the one equations. So additional equation still need. So even though the level changes, but we understand the liquid volume inside the tube didn't change. So we know even though before the rotate, this is before the rotate, we know the height in here and then the height in here. This is before. So totally the height for the liquid is 36 centimeter, right? Even though after rotate, if the liquid didn't flow out, so the D1, even though the elevation changes, but the D1, D2 still need to equal to 36, right? So we have the equation in here. So before and after, the total liquid current height is the same. Because the liquid didn't flow out. Okay, so you have the two equations, and then you know how to solve the D1, D2. So in that way, you can simply 1 plus 2. Equation 1 plus equation 2. So Z1 can cancel out. So 2 times Z2 is equal to 0.317 plus 0.36. Okay, and this is equal to 0.677, and so you know the Z2 is 0.677 divided 2 is around the 0.338 meters, and you just push this number inside the 1 or 2. You can pick up which one you like. So finally, the D1 is equal to 0.022 meters. Okay, so that means after you rotate, the Z1 will become here, and the D2 maybe become here. Okay, so we change it to here, and the decrease in here. Okay, so if we rotate more high speed, maybe the liquid inside the tube will flow out. Okay, but we cannot that means we cannot have the high speed, because the problem will include some fluid outside, and then you don't have this equation. You cannot understand how to solve the D1, D2 elevations. Okay, so this is very important. Usually we need to consider the rotation flow under these problems. If your speed high enough, the flow will flow out. The liquid will flow out. It's not correct. Okay, so this is our final slide page in today. So prepare your cell phone and we move to the Kahoot